audio. There we go. Oh, what you got? Everybody get the attendance sheet already? We good on that? All right. Okay, well, thank you. So before I get into the techniques, which, you know, we spend most of our semester on just, here's a problem, here's how you solve it, right? This is a very problem-solving based course. But before we get into that, it's a good thing for us, and I don't always do this, but it's a good thing for us to like take some time just to talk about the terminology and the, you know, terms and conditions, I say, all right? So like, let's just, and you know, you don't have to write all this down. We're just going to kind of read it together. Usually I would say it's very important to take notes. This is the one day I'm like, it's okay to just kind of follow along with me. So a differential equation is, surprisingly, a equation which involves derivatives. It's like, yeah, okay, but that is actually what it is, all right? You know, of course, it's important to understand the domain of definition, right? If the formulas that define your differential equation have division by 0 at some point, well, then that point's outside the domain, right? Now, for the most part, we're looking at real differential equations. We want real solutions for real problems, but we'll see that complex solutions play an important role in this course. We're going to find there's a number of problems that we have to take a complex approach to get the full generality of like how to find the solution, right? But that's always kind of like a halfway point to the solution. We find a complex solution, and then we'll come back and find a real solution. We'll see that about like 3 different ways this semester. So we're mostly studying ordinary derivatives. What an ordinary derivative is, well, when there's just one independent variable, in this case x, in this case t, right? And so this is like a first derivative, dy dx, right? It's the second derivative. This is just notation at the moment. The nth derivative. Here's the derivative of a vector, right? You guys know this stuff. You've done it. You survived 3 semesters of calculus, right? This is, right? It's pretty boring. Now, so here's an example of a differential equation. Generically speaking, it's some function of the nth derivatives in n minus 1th and all the way up, you know, all the way down to the, so y here is the dependent variable, x is the independent variable, and this would be an example of a differential equation, right? Y prime prime plus 3y prime plus 4y squared. This would be n equals to 2 because the highest order that appears is the second derivative, so it's a second order differential equation. This one would be a kth order differential equation. Now, both of these are what are called nonlinear differential equations because the dependent variable squared appears, all right? N equals 1 is a special case, first order differential equation. We'll be mostly looking at that for the next few days. And in that particular case, it's often convenient to rewrite the, not to write it like this, but instead to write the derivative equals to some other function of x and y, all right? So like, for example, if we have dy dx equals to x squared plus y squared, that function is x squared plus y squared. Or, oh, this is more exciting, dr d theta, r theta plus 7. Well, here our function defining the differential equation is r theta plus 7. Plus 7? Huh. That feels like a typo. All right, so yeah, if you see something, say something. You can always email me if you think, you know, as you're reading the notes and something seems out of place, just send me an email if you're really curious, right? Okay, so here's some other ones. This one is a mix, right? So this one has, these are all still ordinary differential equations, but this would be a system of ordinary differential equations because we have not one, but actually 3 differential equations, and there's one independent variable, time, all right? T we usually think of as time. But you see the dependent variables of x, y, and z, they're all intertwangled, you know? They're all intertwined. I don't have any earthly idea how to solve this system, by the way. It's not hard to write down a system of differential equations that you can't solve. In fact, solving nonlinear differential equations is actually very difficult in general, and we don't have closed form solutions to most of them, right? So like actually finding an explicit, nice solution to a differential equation is a somewhat rare thing. That said, there are like qualitative methods that we can use to still understand like how to find at least approximate solutions to these kinds of things. Although that's probably the sort of thing you might do with like Dr. Wang in like the Math 352 course, perhaps. Dr. Wang is an expert in numerical approximation. So you talk to him if you ever have a real problem about that kind of thing. So a good portion of this course is spent solving the nth order linear ODE. That is a differential equation that has the form, a function, a sub n times the nth derivative, a sub n minus 1 times the n minus 1th derivative, all the way down to the, a sub 0 times y. That's supposed to be a prime there. Man, look at that. Hideous. There's a prime here. Imagine it. So I'll fix it. Okay, yeah. I'm just messing. Actually, it's the one marked. Wouldn't harm too much, right? It would be our secret. Every time I use this, you'd remember it, right? Okay, I'll stop. Anyway, so listen, these a sub n's, they could be numbers, they could be functions, all right? When they're numbers, we completely describe how to solve that problem in total generality in this course. It's actually just a matter of algebra. When they're functions, it's harder, but we have some ideas about that with series techniques, all right? Here is a system of linear differential equations. See, it's everyone is the reason that this is linear is the dependent variables appear without squares or square roots or anything. This t cubed is the independent variable. The independent variable could be a square or something else. It doesn't have to be linear. It's still the linearity of the differential equation refers to the dependent variables, because it turns out, as we study the properties of these, if you have only the dependent variables appearing in a linear way, it's true that the sum of solutions is again a solution, and a scalar multiple of solutions is again a solution, at least for a homogeneous problem. So that kind of superposition principle is the sort of bedrock of what makes linear differential equations interesting, and we'll solve a lot of those. Now, at the very end of the course, the boss fights, they're about solving these kinds of things. Partial differential equations. Partial differential equations involve more than one independent variable. Like here, it has x and y as independent variables. This one's got x, y, and z as an independent variable. Here, phi is the, it could be a temperature function or something. This is known as the Laplacian. It's the divergence of the gradient, if you want a, vector calculus way of thinking about it. And of course, also, Maxwell's equations involve the divergence of the electric field or the curl of the magnetic field, right? The Faraday's law is del cross B is equal to minus partial E partial T. That would be Faraday's law. And so forth. So a partial differential equation is a differential equation that involves more than one independent variable. And those are difficult to solve in general. You might have a whole other course in that, but not here. We don't have that course yet. But I do spend about 2 weeks in here on that at the very end of the course. All right, so here's the basic question that we want to answer in here is, how do we solve a differential equation? That's what we're interested in. Here's a differential equation. What are the solutions, right? So that begs a more fundamental question is, what do we mean by solution, right? So this is what we mean. A solution to a differential equation is a function or a level set for which the given differential equation is a differential consequence of the solution, which is just a fancy way of me saying if you plug the solution into the differential equation, it works. All right? And you probably worked some of these in your calculus class, right? These appear early on in Calculus 1. They're scattered here and there, this idea, trying to pepper your intuition with what a solution is. But here's an example. Y equals cosine x is a solution of y prime prime plus y equal to 0. Why is that true? Well, if we differentiate cosine twice, we get back to minus cosine. So y prime prime is minus y, which means that y prime prime plus y is equal to 0, which is to say that y equals to cosine x is a solution to that differential equation. If we plug it in, it works. By the same token, if we had x prime equals to dx dt and x prime prime plus x equal to 0, well, that also would have solution x equals to cosine t, right? Same pattern, different letters, right? Here, independent variable was x, the dependent variable was y. Notice here, the dependent variable is x, and the independent variable is t. So the role of x and y and t, these are not sacrosanct. They change for different problems. Context matters, all right? Anyway, so what this means? Well, this solution is modeling the motion of a mass moved by a spring without friction, right? This is actually like m equals to minus x, so like the mass is 1 and the spring constant k is 1, right? What I have not explained is where cosine came from. Sine? Well, I mean, okay. That's kind of like, which came first, the chicken or the jockey? I don't know, like, whatever, but sorry, I'm still recovering. But my mom watched it with my kids. My son says that there's a law, any movie that Jack Black is in, he must sing 3 songs. So it's about right. But anyway, Minecraft lore aside, I have not explained how to derive y equals cosine x here. I've just pointed it out to you. It works, right? We will find ways to derive it as we go on, okay? But I'm not there yet. I'm just showing you it works. Checking something's a solution is much easier task than deriving the solution, right, from some other principle. All right, here's another one. If we were given xy cubed plus y squared equals to sine x plus 3, if you differentiate that implicitly, you get this, right? So what that means then is that this equation is an implicit solution to this differential equation, for example. All right. Now here, notice I can't solve for y. I don't know about you, I can't solve for y there. Can you isolate y? You've got y cubed plus y squared equals to sine of x plus 3. Like, I can't. Personally, I can't solve for y there, right? So sometimes we have no choice but to capture our solution in terms of an equation or a level set, as it's known, all right? And in that context, implicit differentiation connects the level set to a differential equation. Here's another one. If we have a function of xy equal to x squared plus y cubed equal to 10, then we can take the total differential of that. Remember Calc 3, we learned about the total differential, so 2x dx plus 3y squared dy. Well, that's the differential consequence of this. So let's see here. So what I'm saying is, if we think of this as a differential equation, then this equal to 10 is a solution to that differential equation. So we can also write differential equations in terms of differentials. All right, this is like a shorthand for writing a differential equation. We'll talk more about this. This is the so-called Pfaffian form of a differential equation. Here's another one. If we had a vector field, x, 2y, 3z, and we look at the path, x naught e to the t, y naught e to the 2t, z naught e to the 3t, in other words, parametrically, x equal to that, y equal to that, z equal to that, if you calculate dr dt, you get this, right? But that's exactly f at x, y, z. It's f of r of t, right? So what that shows you is that if I plug this r into the differential equation, dr dt equals to f of r of t, it works. So this path solves this differential equation for this given vector field. What this would mean geometrically is that the vector field is such that that curve would line up with the vector field, right? The vector field might be like this, and the curve is such that when it goes through that point, the tangent vector to that curve points in the same direction as the vector field. In fact, it matches up directly. This is what's called an integral curve or flow line to the vector field. So if we have a vector field in 3 dimensions, and we're interested in finding flow lines, that is a problem of differential equations. In fact, ordinary differential equations. dx dt equals to x, dy dt equal to 2y, dz dt equal to 3z. Those would be the differential equations I'm trying to solve to find the integral curve, which I've written down here. And we'll look at more of those. So we should talk about solution versus explicit versus implicit. An explicit solution on a subset of the reals, this means subset, and this is like an interval. An interval is just a connected set of real numbers, usually like an open interval or a closed interval, or could go from 3 to infinity or -2 to minus infinity. These are, you can draw it on the number line without lifting your pen, right? An interval. So an explicit solution on an interval for an nth order ODE, here's the nth order ODE. We're using this big function f to sort of just compactly describe it, what that means is if we replace the dependent variable and its derivatives with the actual derivatives of the alleged solution here, phi, like the nth derivative, n minus 1th derivative, and so forth, it equals to 0. So this, again, this is just a precise and explicit, forgive the pun, it's a concrete definition to make clear what we mean by explicit solution, all right? The key here, though, is that we can solve for y as a single function of x. That's what makes it explicit. Implicit, it could be this also, but it doesn't have to be, all right? So like every explicit solution is also an implicit solution, but the converse is not true. Like the one we saw earlier, where you couldn't solve for y cubed. That was an implicit solution. Now, all right, so far I've just described to you some terminology and showed you a little bit about how things work, but we just pulled them from the thin air, right? So can we solve differential equations some other way besides just rote guessing? Well, yes, there are methods, right? So here's the simplest differential equation I could think of. dy dx equal to 0. That's a differential equation, right? How do you solve it? Well, we integrate, right? Integrate both sides with respect to x. The dx's, they be canceling. You get integral of dy is y equal to a constant, right? So if we have this differential equation, we can just integrate it, and there you go. That's the explicit, quote-unquote, general solution. That's all that there is to find there. There's no other functions whose derivative is 0 except for the constant functions. Right? If we're talking about the domain being reals, right? Like you could have a function that's like constant here and constant there with a jump, right? That would still be a solution, but not on the whole real line, right? There'd have to be some point where there's a discontinuity, so we could do that kind of funny stuff. There's more there to be found. But as long as we take the domain of definition to be the real line itself, that's totally general solution. And that's what we're going to do by default here. I'm not going to keep having this discussion. Well, we're assuming that the whole definition is the whole real line. If it were something else, then we could also have these weird jumpy solutions, and like we don't do that. Okay. How about y prime prime equal to 0? Integrate once, you got dy dx equal to constant, right? Integrate again, you got, when integrate the constant, we get x, and of course plus a constant, right? So the general solution of y prime prime equal to 0 is, well, it's a line, right? So you might start to get the feeling, wait a minute, so why is this a course? I just take a differential equation and I just integrate it, right? We're done. What's the problem? Why is that not enough? You know? Why can't we just keep doing this, you know? I mean, obviously, continuing this story, it's fairly obvious that if you were to calculate the general solution of the nth derivative of y with respect to x set equal to 0, you just integrate n times, right? And as you integrate, you keep picking up factors of fractions from each integral, and it builds up a factorial in the first term all the way down to like that, right? So we got that far in the previous discussion. But here would be like the solution of this nth order problem. So we can actually calculate it. Actually, these three boxed equations are very helpful in terms of telling us what we're going to find as a general story. Like a first order differential equation has one constant in the general solution. Second order differential equation, two constants in the general solution. Nth order differential equation, n constants in the general solution. The reason that there's these constants is because there's an ambiguity. It's not enough to specify the derivative. That doesn't give us a unique solution, right? There's a freedom in initial conditions. Like for this one, the one initial condition will do, right? If you tell me the value of y at any x, that fixes the constant, right? But here we have a slope and a y-intercept to fix to pick out a unique line. If we change x instead to t, like time, the initial conditions become initial position and initial velocity. So to calculate, the position, you need an initial position and an initial velocity if we're trying to solve acceleration equal to 0. All right. All right. So moving along here. So as I was just describing, we see arbitrary constants derived allow for different initial conditions which are possible. All right. So in fact, the general solution isn't really one solution. It's actually a set of solutions. All right. This is even true in like calculus 2. Even starting in calculus 1, once we talk about the indefinite integral, to be fussy, we really should inquire set notation, because the integral of f of x dx is actually every antiderivative such that f prime of x is equal to the integrand, right? But I don't know about you, but when I teach calculus 1, I don't make them write that because there'd be like a mutiny or something, right? Instead, it is the common practice that we do what? We write f of x plus c. That plus c is a reflection of this set because that's the form the set has. See, because any two functions that agree on the integrand, that means their derivatives match, and two functions are the same. They have the same derivatives. That just means they differ by a constant. You see, so if we add a constant, an arbitrary constant, to an antiderivative, that's the same as giving the set of all possible antiderivatives, assuming we're working on a connected domain. But again, we don't like to write sets, so we just write f of x plus c. Well, in the same sense here, we write the general solution involving these arbitrary constants, which is a reflection of the fact that it's actually not a single solution, it's a whole set of solutions which are amenable to fixing different initial conditions. That's what we're going to see. All right, so anyway. So the general solution, that's a term we throw around in here, that means a solution which allows for all possible contingencies, right, for the differential equation. So like for this one, y prime prime prime, wait a minute, prime, y prime prime prime, okay, 3, minus 4 y prime prime plus 3 y prime equal to 0. This term, it turns out, has the solution c1 plus c2 e to the t plus c3 e to the 3t, right? We will learn how to derive that in like less than 2 minutes once we learn the technique. It's very simple, actually. But that is actually true. And you notice that there's 3 constants here because this is a third order differential equation. The general solution to this system, x prime equal to minus y prime equal to x, it's actually given by this sum of cosines and likewise sum of sines and cosines. These are actually parameterizations of a circle of radius c1 squared plus c2 squared. That's what this is. You can also have systems of nonlinear differential equations. Those are more scary for me, but here's one we probably could solve this system if we wanted to. Oh, wait a minute. I guess we can't, right? Because if you have this, right, and you have that, then it's hard to have them both at the same time, because to have both of these at the same time is to do what? If those are both true, we've got 0 equal to minus 1, which no matter how much more math you learn, it's still really hard to achieve that, you know? Certainly not possible in our context here. All right. Okay, so I just showed you that integration sometimes solves a problem. The question is, can we always integrate? You know, it's not at all clear. By the way, just to go back up here, this problem right here, right? Why can't we just integrate to solve this? What would happen if we integrate both sides? I mean, you could integrate both sides, right? It would give you y prime prime minus 4y prime plus 3y, because when we integrate, we get rid of 1 prime, equals to a constant. But at that point, we're stuck, you see, because we have y prime prime, and y. So we can't isolate just a derivative to integrate again, because the derivative and the dependent variable are both present. So we can't just integrate, because we're at an impasse. But at the same time, the first integration does show you why there's constants here. So I mean, yeah, there's something there, I guess. But here's a way we can derive that cosine solution I was just showing you guys. All right, so does integration reveal this directly? Well, not quite directly, but we have y prime prime equals to minus y. That's what we're trying to solve, right? So if we integrate both sides, we'd have you know, y prime prime dx equal to integral minus y dx. And at that point, we'd be stuck, because we'd have, like I was just saying, y prime equal to a constant plus the integral of minus y, right? So if I could just follow my own notes, I wouldn't have gone back to the previous example. I'm sorry, guys. I did write these like a couple months ago, in my defense. But all right, so then what? How do you actually solve this? Well, this one, it requires a certain amount of trickery. So suppose we have y prime prime equal to g of x for some continuous function g. Oh man, I'm not solving that yet. I guess I'll come back to it eventually, but maybe not today. So this one we could solve though, right? Because we integrate once, we got y prime integral g, so that would give us this, you know, integrating once, we'd have y prime in terms of the integral of g. And then if we integrate it again, then we'd have the solution, right? Like the solution for this differential equation, y prime prime equal to g, would be y of 0 plus y prime of 0 times x plus this integral of the integral of g of t ds, like this. So for any function g, we could calculate the integral like that. But again, this is a very special differential equation. It had the derivative sitting out there on its lonesome without any other dependent variable derivatives clouding the issue. All right. So how do we solve it if it's not possible, right? Like, what do we do if, you know, it's not the case that you just got the derivative sitting out there, right? Well, that's what we're about to talk about, right? That's where we need the techniques we're going to cover in the next week or so. Let me finish this discussion up here. The other thing to talk about, of course, is initial conditions. That means that they're all given at the same value of the independent variable. In contrast, boundary conditions, that's when you're given data at two different independent variables. So maybe you're given something about the problem when time equals to 0 and something else about the problem when time equals to 1. There really is no guarantee that your solution can satisfy both of those at the same time. Boundary conditions are much fussier. We're going to see that as we study the boss fight problems at the end of the course, all right? But they're interesting. All right, so I think that may be just about it. So here, I talked a little about this already, but just to reiterate, the total differential of a function, if our function has n variables, then we have like partial f1 dx1 plus partial f2 dx2 all the way out to partial fn dxn. This is the total differential, and we can use that kind of notation to like trade. So like this is the regular sort of differentially. I don't know what the regular notation, let's say, right? So this differential equation we could trade, formally speaking, by multiplying both sides by dx to get that. Or we could also rewrite it as that. Okay? This is the so-called Pfaffian form of this differential equation. And there are reasons to prefer this, in the sense that this right here, this presupposes that y is a function of x, right? But there are physical problems where y and x are on equal footing. And in that context, maybe you'd prefer the Pfaffian form because it doesn't presuppose a certain independence or dependence, right? This equation, on the other hand, it doesn't see necessarily the distinction between y and x so much as we study that way of thinking. Like this example, dy dx equals to x over y. Like y equals to 0 is outside the domain of definition, right? We can't have division by 0. But you guys remember from calculus 2 how we solve this, right? We multiply y to the other side, x to the other side. It's separation of variables, integrate both sides. Y squared over 2 equals to x squared over 2 plus a constant. All right, great. Now this you could rewrite as that. It's y dy minus x dx. This is the Pfaffian form of this differential equation. And so here's the difference. Like this, technically speaking, they're not quite the same differential equation because they have different domains of definition. This doesn't allow y equal to 0, but this does. And indeed, y identically equals to 0. Let's see here. I think I could have x identically. I'm trying to remember. I think I could have y equals to 0 here. I would just also need x as constant, right? If y is equal to 0 and x is constant, then this solves that, right? All right, so last but not least, I would point out as a somewhat motivation for this course that pretty much every basic theory of physics at the classical level is defined by some differential equation, all right? Like classical mechanics is essentially the problem of solving the time rate of change of the momentum is equal to the net force. This is a system of ordinary differential equations, all right? Possibly linear, possibly not, depends. If you study Lagrangian mechanics, which is how to do classical mechanics in a more beautiful way that naturally allows for generalized coordinate systems and such, you end up with, again, ODEs. Well, they're ODEs that are based on certain partial derivatives of the Lagrangian with respect to the generalized coordinates, but still it's a system of ODEs, all right? It's a system of ODEs. Electricity and magnetism, right? I'm actually teaching this course this semester where we're basically the whole course is to try to solve these equations. These are Maxwell's equations. They're partial differential equations. E and B are functions of space and time. So there's 4 independent variables. And it involves curls and divergence and current density and charge density, all that. But it is a system of coupled partial differential equations. Special relativity. Again, it uses the same kind of, this is just kind of for fun, but these 4 equations can be written as these 2 equations in terms of special relativistic notation. It's the same system, still a partial differential equation. General relativity, Einstein's field equations are partial differential equations, nonlinear partial differential equations. These are particularly formidable to solve. People have spent their whole career finding numerical solutions through techniques like the Regge calculus and other things. Quantum mechanics at its base is based like basic quantum mechanics, not the really fancy stuff, but the stuff that we've known since like the 1920s. It's based on Schrodinger's equation, which is a partial differential equation. Solving that partial differential equation for the hydrogen atom gives you solutions that define much of the chemistry that we know. All those orbitals and things, those are all solutions from partial differential equation, from Schrodinger's equation, hydrogen-like atom, all that stuff. Now, quantum field theory, the classical field theory which underlies this is actually a nonlinear partial differential equation known as Yang-Mills theory. The rest of it is well past differential equations. So there's some other mathematics there we don't entirely understand, but that's not our problem. I don't get paid enough. But in any event, if a system has variables where the change in one variable or parameter causes the change in one way or another other variables, that means that you can write down a differential equation to describe the system. And what doesn't have this form? Where is it ever the case that the change in one thing doesn't give you the change in something else? Like, think about it. It's just ubiquitous, right? Like, it's everywhere. And so we must understand how to solve differential equations because they're everywhere. So here's a brief course overview, which I'll let you guys read. Basically, to start with, we'll learn how to solve the first order differential equations. Once we're done with that, we flip over to the nth order differential equations. We find the nice ways to solve it. After we're done with the nice ways, we shift over to studying systems of differential equations. We look at this qualitative energy analysis. Then we do this wild thing called Laplace transforms to solve discontinuous problems. And then finally, at the end of the course, we go back and we learn more subtle ways to solve the stuff we did at the start of the course, like mostly chapter 3. And then finally, we study the boss fights. So I have one more, just a little bit more to say today. We write on the board finally. I don't feel like I've done. Oh, well, all right. What? Fortunately, I have the juice. So you guys have a good summer? Are you excited about this semester? No? Yes? All right, good. So we want to solve dy dx equals to f of x comma y. So this is the first order problem, all right? So let me just give you a bird's eye view of what we're going to do like the next 2 class periods, basically. We're going to learn that there's essentially 3 ways to solve this. It's a separation of variables, right? Or it could be the integrating factor technique. or it could be an exact equation. Now, there is actually a little bit more. There's also problems requiring substitution. All right, and once you have a problem that requires substitution, sometimes you make a substitution, and then it takes you one of those other three techniques. All right, but basically, we need to learn how to master these three techniques. Then we should be able to solve a lion's share of the problems that come at us. All right, so that's what we'll be looking at next time, and I think you'll find it very enjoyable. You've already done a lot of it in Calculus 2 if you had it here, and your Calculus 2 instructor wasn't out to lunch, but none of them are, so it was probably fine. Anyway, thanks guys. Have a good day.